Okay, good day. This is Math 130 Intro to Statistics. I am Professor McCullough. This is a lesson 15 on continuous distributions. So let's get right to it. Today we're going to define what a continuous distribution or probability distribution is. We're going to interpret the graphs of normal probability distributions, and we are going to find the areas under the normal curve. So we've done some discrete probability distributions in the previous lessons, and today we're going to talk about what it means to have a continuous probability distribution, and we should define that first. So a continuous probability distribution is a probability distribution of a continuous random variable. Now there are some consequences of that, and one of those things is the fact that since there are infinitely many values for a continuous random variable, we can no longer represent the distribution as a table or a set of values like we did in previous lessons, but we do need to do a graph of some sort to represent the probability distribution. All right, so let's talk about a simple probability distribution that is continuous. A uniform probability distribution is a probability distribution whose values are evenly spread over a range of possibilities. In a uniform probability distribution, the graph will have a rectangular shape. So let's see what that looks like. A probability that a bus will arrive in the next 10 minutes is evenly distributed. So here we have something that is uniform evenly. So first thing, they want to make a graph of a valid probability distribution. So let's do that. So let's talk about what that means. And so here's what I'm going to do. I'm going to create my uniform graph. And again, they tell us right at the beginning that in a uniform probability distribution, the shape of that thing is going to be a rectangle. So along my bottom axis here, I have time. Oops, I want that. Pen, there we go. I'm going to have time, and this is going to be in minutes. This is going to be my x. This is my continuous probability, and it said, let's check and make sure, 10 minutes. So I'm going to put a 10 here. We'll cut it in half. That looks like about half. And we'll go 1, 2, 3. I don't like that. Let's make it a little better. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. And so this will be my probability, my P of x. All right. And we know that any probability distribution, the sum of that probability has to be 1. So if I need to know how tall this probability right here is, I know, and because it's going to be a rectangle, we can just find the area. We know that length times width in this case has to equal 1, because a probability distribution, if you sum up all the probabilities, you have to get 1. So we know that the length is 10, and if we want to get 1 for our value there, whatever that is, because this is going to be my P of x, I'm just going to divide both sides and I'll get P of x equaling to 0.1. So at 0.1, I'm going to draw in this probability distribution here. And this is my uniform probability distribution. And let's make that just a little bit better. There we go. Little OCD there. Sorry about that. But and then let's shade in. We're just gonna shade in this area right here. And so this region represents my continuous probability distribution, and it is a uniform probability distribution. All right, so that's my part 1. Get my pen in here. This is part 1. 2 says, find the probability that the bus will arrive in the first 3 minutes. Well, oops, don't want that. I want to go here. What is the probability that the bus will arrive in the first 3 minutes? So we are just talking about this portion of the graph right here. All right. So all we have to do to figure out the probability that the bus arrives in the first 3 minutes is find this area. And in this case, it's going to be 3 times 0.1, which is 0.3. So we've got a value or a probability that it's going to arrive in the first 3 minutes of 0.3, and that's a valid probability. So I think we're going to be okay there. Find the probability that the bus, only one S there, McCully, will arrive between minute 4 and minute 9. Okay, well, that probability, here is 4, here is 9, and so that thing will be the area in this region right there. Do it in red so we can see. So 2, probability between minute 4 and minute 9 is going to be the area of this particular region here that I've done in red. And there's 1, 2, 3, 4, 5 along the x-axis and still 0.1. And so that value is going to be a 50% chance of 0.5. Finally, number 4 says, find the probability that the bus arrives at exactly 5 minutes. Note, this is an important concept of continuous probability distributions. It's kind of like a trick question. So, probability exactly 5 minutes. Well, in these first 2 examples, we have found regions of the graph. At exactly 5, let's do blue, I suppose, we would have a vertical line with no thickness. So if I still follow the process that I did for these first 2, I have no range of values. I have no thickness to this region. So it ends up being 0 times 0.1 equal to the 0. And so a consequence of that is that anytime you find an exact value, they want just an exact value and not a region of values in a continuous probability, it's going to be equal to 0. So take note of that. Moving on, normal distribution. A normal distribution is a continuous probability distribution for a random variable x. The graph of a normal distribution is called the normal curve and has the following properties. The mean, median, and mode are all equal. The normal curve is bell-shaped and symmetric about the mean. The total end area under the curve is equal to 1. Then, as the normal curve approaches but never touches the x-axis as it extends from the mean, the graph has inflection points at the mean minus 1 standard deviation and the mean plus 1 standard deviation. And the standard normal distribution is a probability distribution with a mean of 0 and a standard deviation of 1. So what does that thing look like? Standard normal curve looks like this. And we can have bell curves that don't have a mean of 0, but the standard curve does. And so the cumulative area is close to 0 for z-scores of negative 3.4. So what they're saying is that if we start here on the left and go to the right, the cumulative area, if we start adding up the areas, as we get closer and closer to negative infinity, this curve tends to get closer and closer but never touches the x-axis. So once you go past 3.5 standard deviations somewhere over here, the curve is so close to the x-axis that the area underneath is almost 0. And so the cumulative area increases as the scores increase. So as we go further this way, the cumulative area gets bigger. So at -2, the cumulative area is right there. As we get to -1, the cumulative area is all of that. So the further we go from left to right, the bigger the cumulative area is. Now the cumulative area for a z-score of 0, now remember z-score is the standard deviations away from the mean. And so a z-score of 0 would be right here at the mean, and so we have half of the area on the left-hand side. The cumulative area close to 1 for z-scores that are close to 3.9. So if I were to come over here, here's my z-score that's close to 3.5, I would have almost all of the area, which has to be 1. All right, now we run into another issue. When we do a uniform probability, we have a simple equation for area for area of a rectangle. It's just length times width. When we have this normal curve, finding the area under this curve becomes problematic because it is in fact curving. So the area under this from -3 to -2 is certainly going to be smaller than the area from -2 to -1 because of the curve. Now, luckily, we have the normal CDF function of the graphing calculator to find this cumulative distribution function. So if we wanted to find the area under the curve left of this z equal to -0.99, so essentially what they're saying is, here is my -0.99. They want us to figure out all of this area right here if that is -0.99. All right, so we're going to grab our graphing calculator and we'll clear all this stuff out. Now the normal CDF function is under, I didn't say that right. Let's go back to here. The normal cumulative distribution function is under this distribution tab, and normal CDF is this. And so if I hit number 2, it says the lower bound is -1 e to the -1 e 99. And so basically that's telling you it is scientific notation where we go 98 decimal place, 98 zeros, and then a point -1. So it's way, way, way over to the left. And we don't even need for our numbers to be that small. We could go like -10,000 and we'll be perfectly fine. But our upper bound, and we're just going to leave that there, but our upper bound is going to be this -0.99. So we're just going to type that in, -0.99. Now, because this is a standard curve, we're going to leave the mean to be 0 and the standard deviation to be 0, and we'll pop through there and we'll hit enter and it fills it in for us, and we'll hit that. Now this is the probability or the area under the curve if you want to go from -infinity to -0.99, and it is 0.161. Oops. So A 0.161. B. It says find the area of the curve to the right of a z-score equal to 1.06. So what does that thing look like? Well, it's a little bit different than what I have here. So 1.06 would be right here, and they want us to figure out the area to the right of that. So we are looking at, so if that's 1.06 right here, we want to figure out what that area is right there. All right, so we're going to use the same function. We're going to again hit second. We're going to hit vars or to get the distribution menu up, and then we're going to hit 2. Now this time the lower bound is going to be the 1.06, and the upper bound is going to be close to infinity. And again, we don't need to make it that big. We can make it 10,000, and the rest of it stays the same. We'll hit enter and we get 1.446. All right, and so let's type that in here. put a 0 there. 0.1446. And you know what? Let's write this. Let me write this in. It would be normal CDF, and it's negative. We didn't. I know we didn't use negative 10,000, but we could have, comma, negative 0.99, comma, 0, comma, 1. So again, mean, standard deviation, and then your upper and lower limit. And for this one, it was normal CDF of 1.06, comma, 10,000. Again, lower and upper bound. And then comma, 0, comma, 1. And if we want to find the area under the curve between a z-score of negative 1.5 and a z-score of 1.25, again, what will that thing look like? Well, if this is negative 1.5 right here, and this right here would be 1.25 right there, we're looking for this area. So it should be fairly large, because it does seem to be most of the area under the curve. And to do that, again, second, distribution, 2 for normal CDF. Well, it'll be at negative 1.5. Oops, I need a decimal place there. And then 1.25 here. The mean and the standard deviation stay the same. Paste that in there, hit enter. 8.275. So C 0.8275, sorry. 0.8275. And for that one, it was normal CDF negative 1.5, comma, 1.25, comma, 0, comma, 1. All right. So let's talk, let's do an example. On a previous SAT, the mean score was 1480 or 1498 with a standard deviation of 316. 4 test scores were chosen at random: 1920, 1240, 2200, and 1390. Find the z-scores for each SAT score. Okay, so remember, let's recall. Z-score is equal to the x minus the mean over the standard deviation. Now, in this particular instance, we have a mean here, since the mean is 1498 and the standard deviation is 316, and they want us to calculate 4 values. I'm going to make a table and use the graphing calculator, because the only value that's changing is the x value. And so I'm going to just write these down. Z of 1920, Z 1240, the z-score for 2200, and the z-score for 1390. And we're just going to do the graphing calculator and have that calculator do it for us. So I'm going to hit clear out all that noise, and I go parenthesis. We'll go x minus our mean, and I've already forgot that. It's 1498. And then we're going to divide that result by the standard deviation, which I remember to be 3 something. It's 316. Okay, so 316. And then we're going to go check to make sure our table is on ask. So second, and then the window to bring up the table set. And then you arrow down, and we'll turn the independent on to ask. And then we'll go second, and then we'll go table. And so we got to enter some of these data points into our calculator for us. And so the first one was 1920. And so its z-score is going to be 1.335. And then the next one was 1240. That's below the mean, so it's going to be negative. And then 2200 It's going to be above the mean, and then again 1390 is below the mean, so we'll get a negative value. And so let's see here. This z-score was 1.335. This one was negative 0.816. And then this one was 2.222, and then this one was negative 0.342. Determine if any of these scores are unusual, and if we recall if we recall the empirical rule, 95% of all of the values are going to be inside 2 standard deviations away. So anything that's more than 2 or less than negative 2 is going to be uh, considered to be unusual, and we only have one value right here. So the value, the z-score for AC, no, it's SAT, for the SAT score of 2020 is more than 2 standard deviations away from the mean. So it would be considered unusual. I know my N's and my U's are starting to look the same. I'm trying to do better. All right, that's all I got today, folks. So, the Marvel fun fact of today: Rocket Raccoon's backstory is pretty horrific. In the first Guardian of the Galaxy movie, in a drunken stupor, Rocket reveals that he is an experiment by scientists who tore him apart and put him back together over and over in the name of science. That's pretty dark, even for a fun movie like Guardians of the Galaxy. Well, that's all I got today, folks. Have a good day.